We will be studying today reflection, refraction, and diffraction. Okay, what is difference between them and how a wave is reflecting, refracting, and diffracting. So all the waves, whether transverse or longitudinal, can undergo reflection at a plane surface, refraction due to change of speed, and diffraction through a narrow gap. Okay, in optics, a transparent material is called a medium. When referring to more than one medium, these are called media, and angles of light are measured from imaginary line called the normal. Now, how to draw a boundary between two mediums? Let's suppose here we are having air, and the other medium is, let's suppose, water, or it may be glass or something. So the first thing we need to do is we need to draw a normal line. Normal line is a line at 90 degree to the boundary between two mediums. All right, so this line is representing a normal line. Now, if a wave is entering, or let's suppose wavefronts are entering from one medium into another, so it refracts. And let's understand this with a simple ray of light. Okay, this ray of light is entering from air into water. So what happens? We'll be studying that in detail later, but it slows down. So as the density of water is greater than air, that's why it is bending towards normal and it slows down. All right. Now, same is the case with waves or the wavefronts as well. Light is also a wave, but it is a transverse wave, a transverse electromagnetic transverse wave. When it comes to water waves or other transverse waves, so what happens if there are, let's say, two mediums, one is deeper and the other one is shallow. Okay, so we are actually doing what we are differentiating that shallow region from deeper region, although they are a part of water, but still they are different in depths. So if they are different in depths, their densities would also be different. And we are considering the shallow region a denser region because the waves cannot oscillate freely over there in the shallow region. That's why we are considering it a denser medium. So obviously, as I mentioned, if a wave or wavefronts are entering into shallow region, what happens? They start slowing down. Okay, and which properties of the wave are changing during this when a when wavefronts are moving from deeper to shallow region. So which properties of the wave are going to change? So there are a few properties we already have studied, and those properties are the wavelength. Number two, the frequency, and number three, the speed. All right. So as I mentioned, um, the speed is going to decrease in a shallow region, and it increases in deeper region. Why? What is the reason if is asked? So shallow is the denser region, and the deeper region or the deeper region is less dense. It is less dense. And we know when a wave moves in a denser medium, It moves slowly, while it moves faster in less dense medium. So this is very important to remember that what happens to the waves are the wavefronts when it enters from more dense to less dense to more dense. Okay, so obviously your speed will be affected. Okay, and here in denser medium, they are, let's suppose if I'm talking about this medium. So this denser medium, in this denser medium, what happens? The particles are there is the waves are experiencing more is experiencing more resistance. Okay, there are more particles are the particles are greater in number, so that's why they are experiencing more resistance, and that's why it is it is difficult for the wavefronts to travel in this medium. And opposite is the case with the less dense medium. All right, so we can see here the definition of refraction. When waves enter a different medium, their speed can change, and this effect is called refraction. So you can define refraction like this, or you can also define it the bending of waves, or you can say wavefronts when it enters from one medium into another. All right. So a wave passes a boundary between two different transparent media and undergoes a change in speed. When a wave refracts as well as a change in speed, the wave also undergoes a change in wavelength, a change in direction. Look, the wave is changing. Now, we know the wave equation, and the wave speed is depending upon frequency times the wavelength. So it means that wave is proportional to frequency, wave is proportional to wavelength. But if they are changing at the same time, like both the frequency and the wavelength are changing proportionally, then obviously the speed would remain the same. But in this case, the only thing which is going to change is the wavelength. Wavelength changes when a wave or wavefronts travels from one medium into another. So what happens to the frequency then? Okay, so keep in mind this is a very important point. Frequency remains constant, right? It never changes. Okay, if a wavefront is entering from deeper region to shallow region, what happens? The wavelength may change. Okay, the wavelength decreases, and we know that speed and wavelength has a direct relation. So if the wavelength decreases, the speed decreases, but the frequency is not affecting the speed. So it means that the frequency remains the same. So if it is constant, they both, okay, the speed is not changing because of frequency, because frequency is constant, right? Okay, so that is the reason the speed is changing because it is changed by the wavelength. Let's say we are taking this region, a shallow region, and this one is a deep region. Okay, and if the wave is entering from this region into the shallow one, so what happens? Obviously, there will be bending, but let me show you an easy example. Let's suppose if you are drawing the wavefronts. Okay, these are the wavefronts, and if it is entering into shallow region, what happens? Okay, you may see this change in the wavelength. Now, what is a wavelength over here? A wavelength is distance between two wavefronts, right? And look at this distance. Okay, so obviously this distance over here is smaller than this distance in the deep region. Like I said, the wavelength is decreasing. Let's suppose if we assume or if we give some values to this wavelength over here, let's say this wavelength over here is 2 meter, and once it enters into the shallow region, it becomes 1 meter. So if the wavelength is 1 meter in shallow region and 2 meter in deeper region, so the frequency is, let's suppose, the number of cycles, right? The frequency is number of cycles or number of waves. Now, the number of waves are two over here, let's say, are three or four or whatever the number of waves are, and the frequency is, let's suppose, 2 hertz. So the frequency will still be 2 hertz over here. Now, if we calculate the speed, speed is equals to v is equals to f lambda, and if we put the values, then frequency is 2 and the lambda in deeper region is 2. Okay, so we would get 4 meter per second is the speed. But for shallow region, this is for deep one. Okay, so for shallow, we will be using the same equation, v is equals to f lambda. But this time we'll be using the frequency value as it is, but the wavelength is 1. So this time in shallow region, the speed is 2 meter per second. So speed is almost half. Why? Because the wavelength is half, so is speed. Okay, so uh, we can read these points over here. Okay, few things you need to know is the speed changes because the wavelength changes, but the frequency remains constant, right? Now, wave changes direction when moving between materials with different densities. All right. The direction of the incident and the reflected rays are also taken from the normal. Okay, the wave slow down, they will bunch together, causing the wavelength to decrease. The wave will also start to turn slightly towards the normal. And if the wave speed, then they will spread out, causing the wavelength to increase. The wave will also turn slightly away from the normal. Okay, now let's see this example over here and let's draw a normal line first over here. Okay, you can see two mediums, and normally we are drawing the wavefronts in water, but this time I'm just changing the mediums over here. One is air and the other one is water, but okay, let's change this into, okay, let me write here that is a deeper region, and this one is a shallow region. Okay, so what happens, by the way, to the wavefronts if I draw the wavefronts over here with a scale, and these are the wavefronts. Let me draw it. Okay, they are entering the deep region with an angle, right? So let me draw with the same angle. Let's suppose that is the angle with which those wavefronts are entering. Okay, and okay, and let's suppose that is what would happen to those wavefronts. Look, it start bending. Okay, so look at the direction. This one, this incident ray is the incident direction, by the way. Okay, so right now we'll be writing here. the direction of wavefronts. Now, after refraction, the direction of wavefronts would be like this. Wavefronts, okay, after refraction. Now, how do we draw these wavefronts? So we are supposed to draw parallel lines over here upon this. Okay, if the angles are given, so you can use the protractor. If they're not given, then you can roughly draw the wavefronts. Okay, but you must be very careful with the wavelength because we know the wavelength will increase in deeper region. All right, so they're bending away. So here it must be like this. Okay, so the wavefronts must be away from each other. Okay, you can see the gap between the wavefronts. It is greater than before. You can see the distance. This wavelength is increased. Okay, initially it was not that much, but right now the wavelength has been increased. Okay, and how they are bending? Look, they are bending away from the normal. Look at this angle. Okay, that is angle of refraction. Okay, let me write this with R. That is R, and this angle is I. Okay, by the way, this bending starts at the boundary. Look, if it enters into this medium, okay, let me draw a wavefront here, and you must find that it is bending away like this. It starts from here, like this, like that. Okay, and this is how they are changing the direction. Now, what is diffraction? The next property are the wavefronts. What would happen to the wavefronts are the waves if they are passing through a small gap. Okay, let's say if there is a gap, okay, that is an obstacle placed, okay, a wooden plank or something is placed in water, and there are two, by the way, two wooden planks. Okay, and this barrier is not letting the water to pass through it. So the only thing happens is when those wavefronts are coming towards that are getting closer to the to this narrow gap, what happens? Okay, once it hits that barrier over here, so there is a small gap, you know, at this point, and let me show you what would happen. Okay, they will start spreading out, but initially they bend themselves and slowly they spread out. Okay, what would happen to the wavelength? Now this time nothing would happen to the speed. Okay, speed remains constant, remains the same, as well wavelength and the frequency. All these properties will remain constant. Okay, nothing would happen to these properties. Like the speed would not change the way the speed was changing during refraction. This time during diffraction, the wave is not going to change its speed. Speed will remain the same. So obviously, if the speed is the same, then speed is depending upon frequency and wavelength. So obviously, the frequency and wavelength are also not changing. That's why the speed remains constant, right? And this bending is like the particles over here. Those wavefronts are made up of small particles, and they produces their own wavelets. Okay, and once we combine, okay, or join those wavelets together, so you would get a bigger wavefront. And you can see those small wavelets combines over here, and the particles in the middle, they move out quickly because they are not getting any resistance. But those particles over here, they loses some of the energy as they hits the barrier, and during this collision with the barrier, are the barrier is providing some resistance. Okay, some friction is there between the particle and the barrier. That's why they get slow for instance, but later on they gain their speed again once they go out into the water again. So this is what happens during diffraction. And the diffraction, when waves pass through a narrow gap, the waves spread out. Okay, this is a definition, simple definition for 1 mark. And this effect is called diffraction. All right, let's see uh, how the bending or the spreading of waves will be affected if we are increasing or decreasing the gap. So you can see over here, this gap over here is very small between the barrier, and you can see more bending. Okay, if if the gap size is smaller than the wavelength, the wavefronts would bend more. Okay, so wavelength is greater than gap size. Point number two, if wavelength is equals to the gap size, still you would get a prominent diffraction or spreading of waves, but this time it will be bend. Okay, the wavefronts will be bending less as compared to the previous case. Okay, but although still there will be a prominent bending, like a moderate one. Okay, now number third, if the wavelength is smaller than the gap size, it means that the gap size is bigger now. Okay, so you would see bending at the edges only. The fronts will bend at the edges. Okay, let me show you how. Look, these factors are mentioned here. These are the factors affecting the diffraction. Okay, so you can read those notes. The extent of the diffraction depends upon the width of the gap compared with the wavelength of the diffraction is most prominent when the width of the slit is approximately equal to the wavelength. Look, so if they are equal, you would get a prominent diffraction, and smaller, even still, you would get a prominent diffraction. As the gap size gets bigger, the effect gradually gets less pronounced until in the case that the gap is very much larger than the wavelength, then the wave no longer spread out. Okay, let me show you the diagrams. You can see over here the gap size of the wavelength is greater than the gap size. Look, you can see the wavefronts are bending more. There's a prominent diffraction. But when the gap size, look at that. If we compare the gap size and the wavelength, how much is the wavelength? The wavelength is almost 0. Yeah, 0.8, right? So the wavelength is, let's say, 0.8. And if we check the length of this gap, it is almost, okay, 1.1.5, right? So this gap size is 1.5. Obviously, our wavelength is smaller than the gap size. Okay, in that case, you would see the wavefronts are bending at the edges only. Okay, these are the edges, and the middle or the center of the wavefront is still passing straight, quite straight, right? And even if we look at that, like if we further increase the gap size, like if it is even very much bigger than the wavelength, then the wavefronts may pass straight. Okay, so you may see those wavefronts are going straight without any showing any spreading. Okay, in that case, this wavelength is very, very smaller than gap size. Okay, so another example is if we place the barrier, uh, we are not placing two barriers now, we are placing just a single barrier at one side. So what would happen? It will, it will be only one end of the wavefront will be spreading, the other will pass straight without any bending. Okay, so if this is our barrier and the wavefronts are coming towards it, so only this part of the wavefront has been stopped. Look, so that's why it is spreading at one end only, and the other one is passing straight because it is not experiencing any resistance. There is no barrier. And if the wavelength is bigger, then you would see still it is bending at the edges. That's it. That is all about diffraction. Okay, that is enough for today. Tomorrow we will be studying a new topic. Thanks and take care.